Of all the objects lurking out there in the cosmos, I mean, are there any as strange or as powerful as black holes?
I don't think so. They're just the ultimate engines of destruction.
Right. Objects so extreme, they basically defy physics, they tear stars to shreds, and of course, they even slow down time itself.
And they're completely invisible, which is the whole thing. Their gravitational power is just, it's beyond imagination. These are things that sit right at the intersection of like pure mathematical theory and this catastrophic physical reality.
And for a long time, even the greatest minds, people like Albert Einstein, they were deeply skeptical that something so outlandish could actually exist.
He hated the idea. He really did.
Welcome to the deep dive. Our mission today is to trace the stunning evolution of how we've come to understand black holes.
Yeah.
We're going to start with their initial, almost improbable discovery as just some squiggles on a piece of paper.
That's right, just math. And we'll follow that thread all the way to the monumental modern evidence that confirms, yeah, they're real.
And not just real, but actually essential to how the universe is put together.
And what's so fascinating is that core contradiction in their story. Black holes weren't seen first. They were deduced.
Right.
They were found as this bizarre, very specific solution to Einstein's revolutionary equations.
Yeah.
A pure mathematical enigma that, as you said, their own father, Einstein, he just could not accept it as real. The implications were just too weird.
But nature is often weirder than we think.
Yeah.
And we're going to trace that path all the way to, I think, the ultimate confirmation. September 14th, 2015.
Oh, yeah, the big one.
A signal that traveled for over 1 billion light years reached us in the early hours of a Sunday morning. And it wasn't light, it was a tremor in spacetime itself.
And that tremor, it was recorded as a little chirp. A sound that got higher and higher, lasted less than a second, but it was just monumental. It opened up a completely new way of exploring the universe.
And it validated Einstein a century later.
It proved that black holes exist and that they smash into each other in these unbelievably violent events that, for a split second, put out more energy than all the stars in the visible universe combined.
Okay, so let's get into this history. To really get how the math led to the black hole, we first have to kind of rethink gravity itself.
Right.
For hundreds of years, everyone was perfectly happy with Isaac Newton. He figured out the laws of motion, he could describe gravity's effects perfectly, but he never actually said what gravity is.
It's that ultimate why question, isn't it? Why does the Earth orbit the sun? I mean, why does an apple fall if there's nothing touching it, nothing pulling it down with a rope? Newton just said it's this mysterious, instantaneous force that acts across huge distances.
And Einstein just completely threw that out.
He did. General relativity changed the question. He turned gravity from a force into, well, geometry.
So how do we visualize that shift from force to shape?
Well, think about that classic physics example. You shoot an apple from a cannon, right?
Hmm.
It makes a curved path back to Earth. But if you could shoot that apple fast enough, say 17,000 miles an hour, its curved path would perfectly match the curve of the Earth. It would just keep falling forever. It'd be in orbit.
That's what the astronauts on the space station are doing. They're not weightless. They're just falling.
They are falling freely along a curved path. And Einstein's beautifully simple idea was this. Mass, like the Earth or the sun, literally causes the space and the time around it to bend or curve.
Like a bowling ball on a trampoline.
It's a classic analogy. And objects in motion, they're just following the straightest possible line through that curved space-time. There's no force. It's just geometry.
So the geometry of space is warped by mass.
Yeah.
That seems like a concept that should pretty logically lead you to black holes, but Einstein didn't discover them.
No, he didn't. And that's maybe the most amazing part of this whole story. Einstein published his papers in late 1915, and he was working on approximations because solving the equations exactly was fiendishly difficult. He thought they only really applied to, slowly moving things, moderate gravity.
Okay, so who cracked the code?
A German astronomer named Karl Schwarzschild. And this is where the story gets really dramatic. Schwarzschild was brilliant, head of the famous Potsdam Observatory.
Right.
But in 1915, he gets pulled out of his academic life and sent to the Russian front during World War I. He was calculating artillery trajectories for the German army.
Wait, so he gets Einstein's world-changing papers while he's in the middle of a war zone.
Exactly. And in a matter of weeks, sitting in a tent with bombs going off, he finds the exact solution to Einstein's equations for the gravity around a single point of mass.
Wow.
Einstein was just astonished when he got Schwarzschild's calculations.
Wow.
He didn't think an elegant, exact solution was even possible.
So the father of the theory couldn't find the exact solution, but this astronomer on the front lines did. What was the conceptual leap he made?
Well, Einstein was looking for a solution that fit the world he knew. You know, a slow, gentle bending of space. Schwarzschild's solution showed something way more extreme. He found that in the math, there was this strange distance from the center of a very concentrated mass. Say, a star that you mathematically squeeze down to a single point.
A boundary.
Yeah,
A specific distance where the geometry just goes haywire.
precisely. This boundary, this strange radius, it meant that if you could pack the mass of the sun into a sphere just a few miles wide,
Which is an insane amount of compression.
insane, the space around it would be so curved that light rays trying to leave would just bend back. They'd be trapped forever. And time itself would seem to stop for anyone approaching it. Schwarzschild had mathematically defined the region of no return.
And that's what we now call the Schwarzschild radius, or the event horizon. It's not a surface, it's a threshold.
It's a one-way membrane. Anything that crosses it is trapped. Not even light can escape. It's this strange cut-off portion of space-time.
But Einstein himself didn't buy it.
Not for a second. His own theory produced this concept, and he just thought it was a mathematical curiosity. He didn't believe nature could ever actually do this, create such an extreme warping of space.
So the idea was basically forced on physics by a soldier on a battlefield, but the greatest physicist of the age just rejected it.
That's the tragic irony of it. And tragically, Karl Schwarzschild got sick on the front, a rare skin disease, and he died just a few months after sending his paper to Einstein.
Wow.
So the man who first defined the black hole never lived to see the idea even begin to gain acceptance. For decades, it just seemed like it was destined to be a weird, beautiful footnote in the history of science.
So let's make that jump. We go from this abstract mathematical idea, the paper black hole from a WWI trench, to the physical, violent reality. If these things are real, how does nature actually make them?
It all comes down to the life and death of stars. And for stars, mass is destiny.
Everything is determined by how big they're born.
Exactly. Stars are born in these huge clouds of gas, and you get tons of small, long-lived stars, and just a few that are incredibly massive and burn out really fast. And the key is a star is stable because of this constant battle.
The inward crush of gravity versus what?
The outward pressure from the energy released by nuclear fusion in its core. That's the engine that keeps the star inflated, pushing back against gravity's squeeze.
And fusion is just, smashing lighter elements together to make heavier ones.
Right. Stars start by burning hydrogen into helium, and then they move on, fusing heavier and heavier elements.
Yeah.
Our sun will stop around helium and just kind of fade away into a white dwarf.
But the really big ones, they keep going.
The most massive stars keep going up the periodic table. They create layers like an onion of carbon, oxygen, neon, silicon.
Until they hit a wall.
The wall is iron. Iron is the ultimate dead end for a star. When you try to fuse elements that are heavier than iron, it doesn't release energy anymore. It actually takes energy.
So the furnace just shuts down?
Instantly. The core becomes mostly iron, the fusion stops, and that outward pressure that was holding the star up for millions of years, it just vanishes.
And with that pressure gone, gravity wins. Instantly and catastrophically.
The collapse is unbelievably fast and violent. Trillions of tons of material rush inward. The outer layers crash down. They bounce off this now super dense core, and that rebound blows the rest of the star apart in a colossal explosion, a supernova.
And that's the moment of truth. What happens to that core left behind depends entirely on how much mass is left.
Right. If it's small enough, maybe less than 1.4 times the sun's mass, the crush is stopped by something called electron degeneracy pressure. You get a white dwarf.
Okay. And if it's heavier than that?
If it's heavier, the electrons are literally crushed into the protons, and they form a solid ball of neutrons, a neutron star.
Yeah.
That's held up by neutron degeneracy pressure. But if the core that's left over is massive enough,
What's the magic number?
the criteria is at least 3 times the mass of our sun. That's called the Tolman-Oppenheimer-Volkoff limit. Once you cross that line, gravity becomes absolutely unstoppable.
So 3 solar masses is the threshold. After that, no known force in the universe can hold it up.
None. Gravity just overwhelms everything. The material keeps shrinking past the size of a neutron star. It shrinks past its own Schwarzschild radius until all of that mass is compressed into a zero-volume, infinitely small point.
The singularity. An
I was-
infinitely small point with infinite density. And that's where our physics just breaks.
That's the failure point.
Yeah.
General relativity predicts this infinite density, but what it really means is that the laws of physics as we know them just stop working at that point. We need a new theory, a theory of quantum gravity, to really understand what's going on there. For now, it's the ultimate mystery locked inside the black hole.
It wasn't until the 60s that this whole idea was really taken seriously, right? Was there a specific moment that changed the mood?
The mood shifted a lot in the late 60s. That's when the physicist John Wheeler, who had been a huge skeptic, started popularizing the term black hole. He borrowed it from the name of an infamous prison in Calcutta.
But the real scientific confidence boost came from actually finding the other kind of stellar corpse.
Exactly. Jocelyn Bell's 1967 discovery of the first pulsar, which turned out to be a rapidly spinning neutron star.
Okay.
So now we had proof that nature could make these incredibly extreme, dense objects, the mass of a sun squeezed into a ball just 10 miles across. So it seemed logical that the even heavier dead stars, the ones over that 3 solar mass limit, they must also exist.
So the conclusion is pretty clear. If a star is born massive enough, say 10 times the mass of our sun or more, it is destined to die as a black hole.
That's its fate. And our galaxy, the Milky Way, we think it's just replete with little black holes. We estimate there could be tens of millions of them out there, just the stellar corpses from generations of massive stars that lived fast and died young.
The theoretical boundary from a WWI trench finally had its physical engine in the cosmos. Okay, so we have the math, we have the violent physics. Let's do the thought experiment. Let's say we have some futuristic spaceship and we decide to go visit a small one, a stellar mass black hole, maybe 10 times the mass of the sun.
Right. This is where you really see how extreme the geometry of space-time gets.
What's the first thing you'd notice as you get close?
The gravitational lensing. It would be bizarre. The black hole's gravity is so intense it warps the path of starlight passing by it, so you'd see distant stars distorted into these weird arcs or smeared into a bright ring right around the event horizon itself.
Like looking at the sky through a cosmic funhouse mirror.
Exactly. And then you get the really mind-bending part, time dilation. As you get deeper into that gravity well, time itself starts to slow down.
Right, because gravity and time are linked.
They are. The closer you are to a massive source of gravity, the slower time flows for you compared to someone far away. So, from our perspective back on Earth, the clock on your ship would appear to be ticking slower and slower and slower.
Okay, so if you on Earth see my time slowing down, what do I see happening back on Earth? That's where it gets weird.
It gets really weird. It's not like time has stopped for you objectively. It's just that your frame of reference is totally different. Because your time is slowed down relative to Earth, you would see time on Earth speeding up.
So I could watch history fly by.
Theoretically, yes. You could watch the future of the universe unfold before your very eyes in a matter of hours or days for you before you cross that final point of no return.
So let's say I decide to go for it. I do a final spacewalk towards the event horizon. What does my crew on the ship see?
As you get closer, the light leaving your body has to climb out of an ever deeper gravity well. And as it struggles against that gravity, it loses energy, its wavelengths get stretched out, it gets redshifted.
Shifts down the spectrum to infrared, then radio.
All the way down. For the observer on the ship, the light pulses from you become nearly infinitely spaced out in time. They would see you appear to freeze, to suspended forever, inches from the event horizon. They could wait for millions, maybe billions of years, and just watch your faded, red-shifted image finally disappear.
But for me, the person actually crossing the boundary.
For you, nothing special happens at the event horizon itself. It's just a mathematical line in space. You'd cross it and just keep falling faster and faster.
And it's not immediately dark inside.
No, you could theoretically see all the light from the galaxy that has fallen in behind you, light that's trapped in there with you. That would be the last thing you'd ever see.
But once you're across that line, you're doomed. You're on a one-way trip to the singularity at the center. And that's where the tidal forces get you.
This is where the fun ends, very quickly. Tidal forces are all about the differential pull of gravity. Gravity gets stronger with proximity, right? So the pull on your feet, which are slightly closer to the singularity, is immensely stronger than the pull on your head.
So you're being stretched.
You are being stretched by a force that is pulling on your feet way harder than your head. This is the famous spaghettification. You'd be elongated, stretched as long and thin as a noodle, and then just torn apart at the molecular level. You disintegrate into your fundamental particles.
And those particles get crushed down into that infinitely small point.
Into the singularity, where, again, our physics breaks down. That's the end of the line as far as we can describe it, though, there's speculation. Some theories suggest that a black hole that's maybe 40 miles across on the outside could be as big as a universe on the inside.
A wormhole or a new beginning.
Maybe. But one thing's for sure, once you're in, you can never get back out, and you can never send a message to tell us what you found.
The theory is beautiful, the thought experiment is terrifying. But back in the 60s, scientists still had this huge challenge. How do you prove something exists when it's, by definition, totally invisible?
Right. It's like trying to prove there's a baseball game happening inside Yankee Stadium without being able to look inside. You can't see the game, but you can infer it's happening by the noise, the crowds, the chaos all around it.
So you look for the effects the black hole has on its environment.
Exactly. And to do that, astronomers had to stop relying just on visible light. WWII led to huge advances that opened up the rest of the electromagnetic spectrum. Karl Jansky found mysterious radio waves from space in the 30s. Then, by using captured German V-2 rockets, scientists flew detectors above our atmosphere and discovered the sky was full of X-rays.
And that just changed everything. Our eyes see this tiny, tiny slice of what's out there. X-rays and radio waves showed this whole new, violent universe.
And the X-ray clue was crucial for black holes, because X-rays only come from things that are incredibly hot. Millions, sometimes tens of millions of degrees. That kind of energy doesn't come from a normal star. It comes from something extreme.
And that led them to the constellation Cygnus, and specifically to Cygnus X-1, the first strong X-ray source they found in that part of the sky. The hunt really began in 1970 with the young English astronomer Paul Merton.
Merton was looking for a very specific thing, a binary star system, two stars orbiting each other, but where one star was visible and the other, the one making the X-rays, was invisible.
And binary systems are common.
About half of all stars have a partner, so it was a good place to start looking.
So he needed proof that this visible star was orbiting a massive dark partner. How do you prove that without seeing the partner?
You use the Doppler shift. It's the signature of movement in light. When a star moves toward us, its light gets squished a little, shifted to the blue end of the spectrum. When it moves away, the light gets stretched, shifted to the red.
Okay.
So Merton looked at the light from hundreds of stars in that area, and he found one, a big blue supergiant, whose light was rhythmically shifting from red to blue, over a perfect period of 5.6 days.
So it was in an orbital dance with something he couldn't see, something dark but massive enough to whip this huge star around every 5.5 days.
Exactly. So the next step, the critical step, was to figure out the mass of that dark object.
Because that's how you tell if it's a black hole or just a neutron star?
Yeah, right. A neutron star can't be more than about 3 solar masses. So this dark X-ray spewing thing had to be significantly heavier than that to be a black hole.
And Merton's first estimate was what, 6 times the mass of the sun?
That was his estimate. And it was an immediate headline, the first black hole detected. But the skepticism was huge because the idea was still so radical.
People didn't buy it.
Not at all. Merton's own boss, the Astronomer Royal Sir Richard Woolley, publicly called the idea fanciful. It led to that famous bet in 1974 between Kip Thorne and Stephen Hawking.
Right.
Hawking bet against it being a black hole, even though he secretly hoped it was. He just didn't think the evidence was solid enough. He finally gave up and conceded the bet in 1990, but the mass estimate was still a bit fuzzy.
Why wasn't it precise? They had the orbit, the speed. What was missing?
The exact distance. They were working with rough estimates, and if the star was closer than they thought, the object could be less massive. To really nail the mass, they had to nail the distance.
And that's where astronomer Mark Reed comes in, much later, using parallax.
Parallax is our gold standard for measuring cosmic distances. You hold your finger out, you close one eye, then the other, and your finger seems to jump against the background. We do the same thing with stars, but our 2 eyes are the Earth's orbit 6 months apart.
So you get this huge baseline, 186 million miles across.
But Cygnus X-1 is 6,000 light years away. The angle of that jump is impossibly small. It's like trying to read the lettering on a dime from 2,000 miles away.
How do you even do that?
You can't do it with one telescope.
Right.
Reed's team used an array of 10 radio telescopes all over the world, from Hawaii to the Virgin Islands. They synthesized them together into one virtual telescope the size of the Earth.
That is just incredible technology.
It's what they had to do. And with that, they finally pinned down the distance. 6,000 light years, with very high precision.
And once you have the distance...
You plug that back into the equations, and it confirmed the mass of the dark object was about 15 times the mass of the sun. Easily over the 3 solar mass limit. It was definitive proof. Cygnus X-1 was the first confirmed black hole.
So what does this system actually look like up close?
It's a violent place. The black hole is surrounded by an accretion disk that's a huge swirl of gas and dust that it's pulling off its partner star.
Like water going down a drain.
A massive cosmic drain. And the material closest to the event horizon is whipping around at nearly half the speed of light.
And the friction from all those particles colliding is what heats it up.
To millions of degrees. That's what blasts out the X-rays that Merton first saw. It's a cosmic vampire just constantly stripping material off its companion star.
But the weirdest part about systems like this are the jets.
The jets are one of the most striking features. These enormous, tightly focused beams of particles and radiation that shoot out from the north and south poles of the black hole, perpendicular to the disk.
Blasting out at nearly the speed of light.
Nearly the speed of light. We think powerful magnetic fields coiled around the black hole are what focus them, like a cosmic fire hose nozzle. But the exact physics is still something we're trying to figure out. What started as a math problem was now a proven, violent, chaotic demon in the sky.
So just when scientists were getting comfortable with these stellar corpses, these 15 solar mass black holes, the universe throws another curveball.
A much, much bigger curveball.
The discovery of quasars in the 1960s. These were just mysterious hotspots in the sky. They were putting out powerful radio energy, and they looked like stars. Hence the name, quasi-stellar radio sources.
And the problem at first was just identifying them. Astronomers looked at their light, their spectral fingerprints that tell you what they're made of, and it was just gibberish. It didn't match any known element.
And the breakthrough came in 1963 with an astronomer at Caltech, Martin Schmidt. He was looking at a quasar called 3C273.
And he finally recognized a pattern. It was the familiar signature of hydrogen, but it was radically shifted toward the red end of the spectrum.
A huge redshift, which in cosmology means one thing.
It means it's moving away from us incredibly fast. This was a legacy of the Big Bang's expansion. These things were just screaming away from us at blinding speeds.
And if they're moving that fast, they have to be incredibly far away. Some of them, like 2 billion light years. And that leads you to the power problem.
Exactly. If something is 2 billion light years away and you can still see it in your telescope, it must be putting out an absolutely astronomical amount of energy.
How much?
These quasars were radiating the energy of 1 trillion suns each second. 1 trillion. There is no chemical reaction, no nuclear fusion process we know of that could possibly explain that kind of power output.
So if it's not fusion, the only engine left that could do that is gravity.
Extreme gravity. Concentrated by a black hole. But we're not talking about a 15 solar mass black hole anymore.
Not even close.
No. To power something like this, the object had to be millions or even billions of times heavier than the sun. This was a whole new category of monster, the supermassive black hole.
Which immediately raises the next question. Do we have one of those closer to home, right in the center of our own Milky Way?
The center of our galaxy is in the direction of the constellation Sagittarius. There's a radio source there called Sagittarius A star, but it's hidden behind 26,000 light years of interstellar dust. It's almost impossible to see in visible light.
But in the 90s, astronomer Andrea Ghez at UCLA decided to take on that challenge. She wanted to pierce through that dust and actually track individual stars orbiting the very center.
This was an incredibly ambitious project. She needed the best technology in the world, like the massive Keck Observatory in Hawaii. But even Keck has to deal with her own atmosphere blurring the images.
Right. The air makes the stars twinkle, which is a huge problem for astronomers.
It is. So her team used this amazing new technology called adaptive optics. They would shoot a powerful laser up into the sky to create an artificial guide star. Then a computer measures how the atmosphere is distorting the light from that fake star in real time, and it sends instructions to a deformable mirror inside the telescope.
A mirror that can change its shape.
Yes, up to 2,000 times a second. It flexes and bends to perfectly cancel out the atmospheric distortion. It basically untwinkles the stars.
And that gave them the sharpest images ever taken of the galactic center. They made a time-lapse movie over 2 decades. What did it show?
The results were just astounding. You can watch it online. You see these stars, especially one called S2, whipping around the core in these tight, fast orbits.
Fast.
Unbelievably fast, up to 10,000 kilometers a second. That's over 20 million miles per hour.
Wow.
That kind of violent motion proved there had to be something incredibly massive right at the center, yet completely dark.
And by applying basic orbital mechanics, they could calculate the mass of that dark object.
And the mass they calculated was staggering. 4 million times the mass of our sun, all packed into a space no bigger than our solar system. That was the smoking gun. Definitive proof of a supermassive black hole sleeping in the heart of our own galaxy.
So if we have one, is that a fluke, or are these things common?
That was the next question. So astronomers, a group called the Nukers, started using the Hubble Space Telescope to look at the centers of other galaxies.
But you can't track individual stars in distant galaxies, can you?
No, so they had to look at the average speed and motion of the stars in the core and then try to build a computer model that could replicate what they were seeing.
What did they find?
They found that their models never worked. They couldn't explain the motions they were seeing with just the mass of the visible stars and gas. The models only matched reality if they added an enormous invisible mass right at the center of the galaxy.
A supermassive black hole.
Every time. Virtually all of the 36 galaxies they studied required one. So the thinking now is that every large galaxy probably has a supermassive black hole at its core. They're a fundamental part of how galaxies are built.
Just to get a sense of the scale, what about our neighbor Andromeda?
Andromeda's central black hole is a true giant, about 100 million times the mass of the sun.
100 million.
If you drop that into our solar system, its event horizon would swallow Mercury, Venus, Earth, and Mars. Jupiter would be gone.
That is just terrifying.
Because it's spinning so fast, it doesn't just curve space-time, it actually twists it and drags it along for the ride.
The lensing must be insane.
So intense that if you were close enough, you could literally look straight ahead and see the back of your own head because light would be bent in a complete circle around it.
So we have this huge size difference. Stellar mass black holes are, maybe 15, 20 times the mass of the sun. Supermassives are millions or billions. How do they get so big? They can't all come from just one star collapsing.
No, they grow. They pack on a weight over cosmic time. And we think there are 2 main ways they do it. There's slow feeding, and then there's catastrophic gorging.
Okay, so the slow feeding is what we call accretion.
Right. That's the process we see in Cygnus X-1. Gas and dust spiral into the accretion disk. They slowly lose energy, get closer, and then fall across the event horizon, adding a little bit of mass at a time. It's a steady way to grow.
And the second way is much more violent.
Gulping.
Gulping. Tidal disruption events. This is when an unlucky star just happens to wander too close.
And it gets ripped apart.
The tidal forces don't just pull it in, they flay a star layer by layer. It gets stretched out into this long noodle of hot gas. And that kicks off a huge feeding frenzy that can last for, 10 years, where the black hole just devours most of the star in one go.
But even with nibbling and gulping, there's still a timing problem, isn't there? How do you explain the giants we see in the really early universe? That's the big conundrum. We can see quasars that existed only a few 100 million years after the Big Bang, and there were already billions of solar masses. How do you grow that big, that fast?
Because there's a speed limit on how fast they can eat, right? The Eddington limit.
Exactly. This is a critical constraint. As the black hole feeds, the accretion disk gets incredibly hot and bright. That's what a quasar is. And the light and radiation blasting out of that disk actually pushes back on the gas that's trying to fall in.
So the black hole's own dinner is pushing away more food. It's a self-regulating system.
It is. If it tries to eat too fast, the radiation pressure gets so strong, it just blows away its fuel supply. It quenches its own growth. So given that speed limit, it seems impossible for a black hole to go from a small stellar seed to a billion solar masses in that short amount of time.
So how do you get around that?
The leading idea is a mechanism called direct collapse. The theory is that in the very early universe, these enormous, pristine clouds of gas could collapse under their own gravity without ever forming stars first.
So the whole cloud just collapses straight into a black hole.
It collapses into a massive vortex like a giant bathtub drain. And this process creates a black hole seed that's already huge from day one. maybe 10,000 to 100,000 times the mass of the sun.
It gives it a massive head start.
A necessary head start to grow into the giants we see so early on.
And these supermassives, they're not just sitting there eating. They have this deep connection with their host galaxies.
It's a profound symbiotic relationship. We see this clear correlation. The bigger the central black hole, the bigger the bulge of stars around it in the galaxy, they seem to grow up together.
And the black hole acts like a thermostat for the whole galaxy.
It does. When it's actively feeding as a quasar, it blasts this huge amount of energy out into the galaxy's gas halo.
And that energy heats up the gas.
It heats it up so much that the gas can no longer cool down and condense to form new stars. So the black hole effectively quenches star formation. It decides whether its host galaxy keeps growing or if it stagnates and becomes a red and dead galaxy.
So they're not just passive objects. They are key players in how the entire universe is assembled.
Absolutely key players.
Okay, so we've established they're real, they're massive, they're fundamental. But now we come back to the ultimate proof. The final, most exotic validation of Einstein's entire theory, gravitational waves.
This was the holy grail of 20th century physics. Einstein predicted that when huge masses accelerate violently, like two black holes spiraling into each other, they should create ripples in the fabric of space-time itself.
Not ripples in space, but ripples of space. A literal squeezing and stretching of space.
Traveling at the speed of light. But the effect was predicted to be infinitesimally small.
How small are we talking?
So small. It's almost unimaginable. A catastrophic event a billion light years away would change the distance between 2 points on Earth by less than the width of an atomic nucleus.
So how on earth do you build a ruler precise enough to measure that?
That was the challenge that the physicist Ray Weiss took on. His background was actually in reducing noise and hi-fi music systems, and he came up with this ingenious idea. You can't use a normal ruler, you have to use light.
And that idea became LIGO, the Laser Interferometer Gravitational Wave Observatory.
That's right. The concept is actually pretty simple. You fire a laser and you split the beam in two. Half the light goes down one long arm a couple of miles long, and the other half goes down a perpendicular arm.
They hit mirrors, they reflect back, and they meet up again at a detector.
And here's the clever trick. You tune the arms so that when the two light waves come back and meet, they're perfectly out of phase. They cancel each other out completely.
So if everything is perfectly still, the detector sees nothing. Total darkness. You've set a trap.
The ultimate noise trap. But if gravitational wave passes through, it will stretch one arm and squeeze the other by a tiny, tiny amount. That disrupts the perfect cancellation. The beams are no longer perfectly out of sync, and a little flicker of light hits the detector. The trap has sprung. You've detected a ripple in space-time.
The technical challenge there must have been unbelievable. You have to filter out every possible vibration on Earth.
LIGO is one of the most complex machines ever built. They had to deal with so much noise. Seismic noise from trucks driving miles away, acoustic noise from the air itself. They had to put the whole thing in a near-perfect vacuum.
And even quantum noise.
Even the random jiggling of the mirrors from quantum fluctuations. And to be absolutely sure a signal was real and not just a local glitch, they built two of them. One in Louisiana, one in Washington State, 3,000 kilometers apart.
A real signal would have to hit both detectors with a very specific time delay.
Exactly. And then came the detection. It was the early hours of Sunday, September 14, 2015. The detectors were still in their final testing phase. A scientist named Robert Schofield was running calibrations. He was exhausted.
And he decided to knock off 40 minutes early.
His laziness, as he called it, was pure luck. If he'd stayed, the machine would have been in a different mode and might have missed it. 40 minutes after he left, the most powerful gravitational wave ever detected rumbled through Earth. It hit the Louisiana detector first, then the Washington one precisely 7 milliseconds later.
And the signal was so clean you could see it by eye.
It was so strong you could just see it in the raw data. A beautiful waveform that lasted less than a second. It started slow, then got faster and higher in frequency and louder in amplitude. A perfect rising chart.
The exact signature predicted for two black holes spiraling together.
It was the final dance of two massive black holes. One was 29 times the mass of the sun, the other was 36. They merged into a single bigger black hole.
And 29 plus 36 is 65. But what was the final mass?
The final black hole was 62 solar masses. The missing 3 solar masses were instantly converted into pure gravitational wave energy. In that tiny fraction of a second, that merger put out 50 times more power than all the stars in the entire visible universe combined. It was the most powerful event humanity has ever witnessed.
And that discovery got the Nobel Prize. It proved black holes merge, and it was the ultimate validation of general relativity. We had finally learned how to hear the universe.
And that was cemented in 2017 when they saw and heard the collision of two neutron stars. This new era of multi-messenger astronomy has just opened up a whole new window on the most violent and energetic events in the cosmos.
What an incredible journey. From a pencil scribble in a WWI trench, this abstract idea of a point of no return, all the way to confirming these cosmic giants like Cygnus X-1 and the one in our own galaxy, and then finally hearing the universe ripple from their collisions a century later.
And the story isn't over. The mystery continues. Our new tools are pushing the limits of what we can even do. The Event Horizon Telescope is trying to take an actual picture of the black hole's shadow at the center of the Milky Way.
To actually see the event horizon for the first time.
A direct image of that donut-shaped silhouette. It's an incredible endeavor.
And we have the James Webb Space Telescope, which can see in infrared, so it can look back to the very dawn of time.
Exactly. It's aiming to solve that mystery of how the first supermasses got so big so fast. It might be able to see that direct collapse process in action.
The reality is, the number of black holes is just going up. Stars collapse, they feed, they merge, they're getting bigger, and they're shaping the galaxies they live in.
They really are the architects of galactic evolution in a way. The cosmic assembly line is, in part, regulated by them.
So we'll leave you with this final provocative thought to chew on. Black holes, these ultimate engines of destruction that swallow everything, they might not actually be eternal.
Right. There's a process, hypothesized by Stephen Hawking, that suggests they slowly radiate away their mass over unbelievable timescales.
So untold trillions upon trillions of years from now, after the last star has died and the last bit of matter has crossed their event horizons, they might just slowly shrink and then vanish from reality completely.
Their power, their mystery, and their slow eventual evaporation will probably continue to challenge our science and our imaginations for a very, very long time to come.